Welcome to this lecture number 35 on the NPTEL course on fluid mechanics for undergraduate chemical engineering students. The topic we are discussing is momentum integral equation approach to understanding forces at high Reynolds numbers on solid surfaces within the boundary layer approximation. Okay. So, we already understood that very close to a solid surface there is a thin region where the fluid velocity varies very rapidly at high Reynolds numbers, and because of this high velocity gradients, viscous shear stresses become dominant very close to solid surfaces even at high Reynolds numbers. So, in order to predict what are the forces on solid surfaces, it is necessary to solve in principle the Navier-Stokes equations within the boundary layer, but we will not do that in this introductory course. Rather, we will take a simplified approximation. We will take a tiny width dx, okay, tiny distance dx along the length of a plate. For example, we argued in the last lecture that even if you have flow past a streamlined body like an airfoil, okay, locally, since the boundary layer thickness is very small, locally this surface is going to appear like a flat surface. So, that is the reason why we are focusing only on a locally flat surface, and so essentially we have a fluid flow past a flat rigid plate, and then there is a boundary layer because of the fact that the fluid velocity has to go to 0 velocity at the surface of the plate. Now, the boundary layer thickness in general is denoted by the letter delta, and we are going to define how the boundary layer thickness is defined we are going to explain how the boundary layer thickness is defined shortly, but in principle it could be a function of the distance along the plate. So, x is the flow direction and y is the direction perpendicular to the flow, okay, normal to the plate. Now, we consider an infinitesimal control volume A, B, C, D, and then do an integral momentum balance. The integral momentum balance simply says that the momentum flux, net momentum flux due to inflow and outflow through these three phases of the control volume must be equal to the net forces acting on the control volume. The momentum flux can enter the control volume through the phase AB, leave the control volume through phase CD, but it can also, since fluid is flowing like this is just the edge of the boundary layer, it is not a streamline. So, fluid can enter the boundary layer through the surface BC also. So, we had derived the mass conservation equation for this control volume in the last lecture and related the various mass fluxes, and so the momentum can enter through all the three phases. Along the phase AD, the bottom surface, it is a rigid surface, fluid cannot come in through the phase AD because there is the no penetration boundary condition at the surface AD. Now, the forces that act on the various phases are, okay, firstly the pressure force, okay, along the phase AB, the pressure force will be in the plus x direction. Along the phase CD, okay, the pressure force will be in the minus x direction. Okay, the pressure force will act here in the plus x direction, pressure force will act here in the minus x direction. And then there are also pressure forces that act on this curved surface, which we will take as the average of the pressure between these two stations and then multiplied by the projected area. Okay, this is something that we are familiar from fluid statics on how pressure forces act on curved surfaces. Finally, at the surface AD, the viscous shear stresses by the viscous drag by the plate on the fluid will act in the minus x direction. Now, if we account for all these things, we ended up with this final differential equation in the last lecture, which relates the wall shear stress tau w, the force per unit area, is equal to du dx integral 0 to delta rho times capital U minus small u dy plus d dx, delta is in general a function of x, of 0 to delta of x rho u capital U minus small u dy. Okay. Now, just to again familiarize you with the notation, this is the free stream potential flow velocity profile outside the boundary layer, okay, and the small u is the velocity profile inside the boundary layer, velocity profile inside the boundary layer. Okay. And the same notation goes here also. Notice that the boundary layer thickness is in general a function of x. So, therefore, even if you integrate this with respect to y, ultimately the boundary layer thickness is also a function of x. So, this d dx will also depend on the upper limit of this integral. Okay. Now, in order to proceed further, okay, I am going to simplify this even a little bit like I did in the last lecture. So, I am going to write this as d dx of u squared. So, if you look at this expression, I have u here. So, I can write this as d dx of okay. So, let me do it step by step. So, I am going to pull out capital U here. So, I get, let us take the second term first, d dx of integral 0 to delta of x rho u capital U times 1 minus u by capital U, okay, and that is the first term, okay, and dy, sorry, that is this term. So, let me first focus on the second term first, okay. So, let me simplify this further and then plus the other term, which we will come to in a minute. If you simplify this further, I can write this as delta x, okay. Now, I can divide and multiply it by u, which will give you this format, and I can pull this u outside the integral, because the integral is merely a function of y. So, this becomes rho u by u times 1 minus u by u dy. This is the second term, okay, which further simplifies here. Now, the first term can be simplified as follows. If you look at the first term, you have u du dx. Okay, so, I can again pull out a factor of capital U and write this as du dx times integral 0 to delta, okay, u times 1 minus rho times 1 minus u by u dy. So, if you look at this term, so I can pull out u out. So, I will get a factor of u divided by u, and since this capital U is a function of x only, I can pull this outside the integral and write it outside. That yields us the final expression for wall shear stress is d dx of u squared integral 0 to delta of x rho u by u times 1 minus u by u dy plus u du dx. Since u is independent of y, we can pull it outside the integral 0 to delta of x rho times 1 minus u by u dy. Okay. So, this is the final expression for wall shear stress. Now, if I tell you what is this velocity profile within the bound layer, we can do the integration and then we can find an expression for shear stress, but this is not yet known. This is not known. Okay. So, we have to make some approximations in order to solve this equation. Okay. Before I spell out what these approximations are, let me first tell you what are the definitions of boundary layer thickness, various definitions. So far I have not rigorously defined the boundary layer thickness. The first definition is called the disturbance thickness, delta, normally denoted by the letter delta. What it essentially means is the following. Suppose I draw the velocity profile in flow past a flat plate. Okay. Now, the velocity will be free stream velocity far away from the flat plate, and it will go to 0 at the flat plate, at the rigid surface itself. But the way in which the velocity approaches the free stream velocity is not abrupt, it is only gradual, or it is asymptotic. So, there is no single point where the velocity is exactly equal to the free stream velocity, it slowly approaches the free stream velocity. Therefore, we can define delta as that. Suppose you ask the question, at what thickness is u, the velocity in the bound layer is 99% of the free stream velocity. That is called the disturbance thickness. Okay. So, one could have different definitions. Somebody could say at what distance it is 99.9% or simply 90% and so on. There could be variations, but they are all in a sense there is some arbitrariness in the definition of the disturbance thickness, but once we all agree to this convention that it is 99%, then that is the distance over which the velocity varies from 0 on the bottom surface, that is the rigid plate, to 99% of the free stream velocity, because it will take a very long distance to it since the approach is asymptotic, it will take an infinitely long distance to approach, truly speaking, the actual free stream velocity, but you can approach 99 or 99.9% or 99.99% okay, fairly quickly, and that is a matter of definition. Okay. So, the other definition is what is called the displacement thickness. We need all the definitions shortly in our calculation of the shear stress. That is the reason why we are going through this discussion. Now, imagine if we had no boundary layer, the flow velocity is the free stream velocity, let us say it is a uniform velocity, then the mass flow rate is essentially, or mass flow rate per unit area is integral 0 to infinity rho u dy times w is the width. Okay, this is the mass flow rate, mass per unit area. Okay. Now, the actual mass flux is not the same, because if I were to draw the actual velocity profile, it is going to look like this. Okay. So, there is a region of deficit, okay, that is there in reality. This shaded region is the mass deficit, because that much is not flowing, which would have happened if the velocity profile was uniform right through. So, this shaded region is the mass deficit. Okay. So, the actual mass flux is actually integral w 0 to infinity rho small u dy, because this is the actual velocity profile, the boundary layer velocity profile. Boundary layer. Okay. So, now the way in which we envisage or we define the displacement thickness is, so essentially it is almost like what the net effect of the boundary layer is almost like lifting the plate to some distance, so that after this distance the flow is uniform, and the actual flow rate, which is obtained by combining integrating this curve, is obtained by simply taking u times this distance. Okay. So, essentially that is what we are saying, that the net effect of the boundary layer is as though it is trying to lift the flat surface, so that the mass deficit is accounted for. Okay. So, how do we do that? We are going to set the losses equal. Suppose you call this thickness delta star. Okay. This mass deficit must be equal to this mass deficit. That is the way we are defining delta star. So, the mass deficit due to the lifting of this imaginary surface by an order delta, by an amount delta, is simply rho u delta star w, but that must be equal to integral rho u rho times capital U minus small u dy, because capital U minus small u is the deficit. If you remember, this is the yellow profile is small u here, and the blue profile is capital U. The difference is this deficit, which is shaded in, this is the deficit region, okay, shaded in yellow. Now, we are equating this deficit to this deficit, thereby obtaining a definition of delta star. So, delta star, and sure enough there is a w here which will cancel in both sides. Okay. So, delta star is nothing but integral 0 to infinity 1 minus u by capital U dy, or delta star is integral, since okay, if you look at these two curves, they are almost the same after a point, okay, after some point of the order delta star itself, they are almost the same. So, we can take that distance as delta, which is the disturbance thickness. So, I can remove infinity in this integrand in the upper limit of the integral, to delta itself. So, delta star is approximately 0 to delta 1 minus u by u dy. Okay. This is called the displacement thickness, which is essentially the idea here is that the net effect of having a bound layer is that it tends to reduce the mass flow rate by a certain amount, and so therefore, in effect you can imagine that in order to calculate the same mass flow rate from the potential flow velocity profile, it appears as though you have to lift the solid wall by a certain amount. The amount to which you lift is called delta star, that is the displacement thickness. So, the reason why it is called displacement thickness is because this essentially means that you are displacing the plate by a certain amount. The other definition is momentum thickness. Other definition of thickness of bound layer is momentum thickness, usually denoted by the Greek symbol theta. Okay. Now, instead of worrying about the deficit in mass, here we are now going to talk about the deficit in momentum. So, the question we are asked, the definition is in that sense very much similar in spirit to the displacement bound layer thickness definition, wherein you worried about the amount of the thickness by which the plate must move in order so that the deficit in mass is taken care of. So, here we are going to worry about the deficit in momentum. Okay. So, without the bound layer, the momentum flux without the bound layer is nothing but integral 0 to infinity. Momentum flux is simply mass flux times the actual mass flux, which is rho u, times capital U dy times W. Okay. So, with the bound layer, the actual momentum flux is W 0 to infinity, okay, rho u squared dy. Okay. So, the deficit is simply, so imagine that, okay, imagine that you are lifting the bound layer, okay, this is the actual surface of the plate. Okay. Now, imagine that you are lifting by an amount theta, so that the approximate momentum flux, the momentum flux calculated from potential flow up to this distance is the same as the actual momentum flux, okay, carried by the bound layer. So, this is the momentum flux, okay, that is lost, okay, by displacing, that is lost here, okay, because you have displaced the plate by an amount, the surface by theta. Okay. And that must be equal to the difference between the momentum flux without the bound layer, and this is the momentum deficit, because this is assumed without the bound layer, this is assumed with the bound layer. So, by equating the two, we will get rho u squared theta w. This is the momentum deficit by lifting the plate, displacing the plate or the rigid surface by an amount, and this is nothing but rho times u times capital U minus small u dy. Now, therefore, theta is essentially integral 0 to infinity u by small u times 1 minus u by capital U dy. Again, to remind you, small u is the velocity profile in the bound layer and capital U is the potential flow velocity profile outside the bound layer. Velocity. Okay. So, we have now therefore three definitions, and likewise we just as we did before, we are going to replace the infinity in the integral by the displacement thickness delta. So, theta is approximately equal to u by u dy. Okay. This is the definition of momentum bound layer thickness. So, you had now 3 definitions. You have delta star, the disturbance thickness, delta the displacement thickness, and theta which is the momentum thickness. Okay. These two are called integral thicknesses because they are obtained as an integral of the velocity profile. Okay. The mass displacement thickness and the momentum displacement thickness are called the integral thicknesses, while delta star is simply the distance it takes for the velocity profile to reach 99% of the free stream velocity. Okay. So, now therefore, we are going to rewrite the momentum integral equation. So, let us go back to the momentum integral equation and rewrite it in terms of the newly defined bound layer thicknesses. The momentum integral equation was simply tau w is d dx of u squared integral 0 to delta rho times u by u times 1 minus u by u plus u du dx times integral 0 to delta rho times 1 minus u by u dy. After using the definitions of the momentum and displacement thickness, we get this is simply nothing but d dx of u squared theta, okay, plus delta star u du dx. Okay. So, this is like this is an ODE, or it is an ordinary differential equation in x, and it has to be solved to find what is the shear stress. Okay. Now, let us look at a special example. Let us look at a particular case which is one of the classic cases in bound layer theory. You have flow past a uniform flow past a flat plate, flat surface, rigid surface. So, imagine that outside the bound layer the flow is uniform, that is no pressure gradient in the potential flow. Okay. So, this is the uniform flow case. So, u of x, a constant velocity u independent of x, and dp dx is 0. These are the two conditions. Okay. So, tau w essentially becomes, since if u of x is capital U, then du dx is 0, it is independent of u. So, the wall shear stress expression just written here, this term will go away, okay, because du dx is 0. So, essentially what you will have is tau w by rho is d dx, sorry, we will just have this expression. Since u is constant, you can pull this out also. Okay. Now, therefore, tau w by rho is written as simply written as, so we can write tau w as rho u squared d theta dx is nothing but rho u squared d dx of integral 0 to delta u divided by capital U times 1 minus u divided by capital U dy. Now, to proceed further, we need to know what is the function small u, what is the velocity profile in the bound layer. Of course, we have not solved for it, so we have to make an approximation. Okay. Usually, it turns out that within the boundary layer there is a similarity solution, in the sense that the velocity profile u by u is nothing but a function only of y divided by delta of x. Okay. So, remember that delta is a function of x here. Okay. So, velocity profile in the bound layer is generally a function of both x and y, but the similarity solutions puts a constraint on how it is a function of x and y. It is a function of x and y only through this combination y divided by delta of x. So, that leads to some simplification. So, you write tau w, now you define a new variable eta is y by delta and transform this equation as rho u squared d delta dx integral 0 to 1 u by u times 1 minus u by u d eta. Now, in order to, so essentially we have to solve this for delta of x, okay, in terms of w tau w. So, in order to do that, we have to first prescribe a form for u by u. Okay. Since u by u is a function only of y by delta, we can stipulate this function as follows using the boundary condition that at y equal to 0, small u must be 0, no slip condition. Y equals delta, small u is exactly equal to capital U. That is an assumption, because although it is only 0.99 or 0.99 times capital U, we are making an error here, but it's an approximate solution here. So, y equals delta, we are saying that du dy is 0, that is the velocity profile as you approach the edge of the bound layer, it becomes independent of the y direction, it becomes a flat profile. So, once you assume a function for y, for u, I am sorry, that satisfies all this. So, let us assume u is a polynomial of the form a plus by plus cy squared. You have 3 constants, unknown constants a, b, c, and you have 1, 2, 3 equations. Once you solve for this, we will get a functional form for u by u. U by u becomes 2 times y divided by delta minus y divided by delta squared, or u by u is nothing but 2 eta minus eta squared minus eta squared. Okay. So, once you substitute this back in here, we can now integrate this expression and get an expression for tau w. Okay. Now, tau w is nothing but mu times partial u by partial y evaluated at y equals 0. Okay. So, now since we have everything in terms of eta, we write it in terms of, and capital U by small u by capital U, we write it in terms of y by delta times delta evaluated at y by delta is 0. This is nothing but tau w is mu u by delta times d of u by u divided by d delta evaluated at eta equal to 0. Okay. So, tau w is nothing but mu u by delta times, you have to set the derivative of 2 eta minus eta squared. So, u by u is 2 eta minus eta squared, d of u by u divided by d eta is nothing but 2 minus 2 eta. If we evaluate it at eta equal to 0, this becomes simply 2. So, we will get the answer 2 mu u by delta, that is the shear stress. Now, we have to substitute this back in the integral momentum equation. Out here, instead of tau w, we are going to write 2 mu u divided by delta, and we are going to substitute for u by u the profile 2 eta minus eta squared everywhere here. Okay. And then we will get a closed form expression for delta. Okay. So, we will just do the algebra. We already had tau w is rho u squared d delta dx times integral 0 to 1 u by u times 1 minus u by u d delta. Okay. So, 2 mu u by delta is nothing but rho u squared d delta dx, okay, times integral 0 to 1 2 eta minus eta squared times 1 minus 2 eta plus eta squared d eta. Once you solve this expression, you will get delta squared by 2 is nothing but, okay, 15 mu by rho u x plus c. So, now let us assume that at the leading edge of the bound layer, at the leading edge at x equal to 0, the bound layer thickness, the fluid is just hitting the flat plate at x equal to 0. So, at x equal to 0, we are going to assume that delta x is 0, that is the bound layer thickness just starts from 0 value. So, the constant is fixed to be 0. So, you get, okay, delta therefore is square root of 30 mu x by rho u, or if you divide delta divided by x, the local distance from the x is actually the distance from the leading edge of the bound layer. So that becomes square root of 30 mu by rho u x. This is nothing but 5.48 divided by the local Reynolds number, which is defined as rho u x divided by mu, where x is actually the distance from the leading edge of the bound layer, okay, from the distance of the origin of the plate. Okay. So this is the Reynolds number. Now the wall shear stress coefficient is defined as tau w by half rho u squared. This is called the skin friction coefficient. Okay. So this is nothing but, now I know what is tau w, which is 2 mu u by delta divided by half rho u squared. Okay. So Cf is nothing but, now after substituting what is delta, I will get 4 mu by rho u delta. Cf is nothing but 4 mu by rho u x times x by delta. So Cf is nothing but 4 times 1 over Re x, the local Reynolds number, times x by delta is nothing but square root of Re x by 5.48. So Cf is nothing but 0.73 divided by square root of Re x. Okay. So this is the expression for skin friction coefficient, which is the non-dimensional shear stress exerted by the fluid on the wall. Okay. So this is an example of how one can get from reasonably simplifying assumptions that the velocity profile is simply a polynomial of the form a constant plus something times y plus some other constant times y squared, and fixing those constants by physically motivated boundary conditions, then we can actually solve for the momentum integral equation and get an expression for the force exerted, okay, on a flat plate per unit area. Now if you want to know what is, and that itself is a function of the distance from the origin of the plate, therefore if you want to have a force exerted on an entire plate, you have to integrate the stress over the distance of along the plate from 0 to L. Since it is a function of x, you have to integrate this from 0 to L, and that will give you the force. Okay. So this tells you in a very simple way how bound layer ideas, okay, can be used to find forces on plates. Okay. Now the same thing can be carried over to more complex objects. Okay. Now here we took the simplest possible case, namely force on a flat plate. The same thing is valid if you consider even an airfoil, because locally the bound layer is actually flat. So you can integrate over the contour of the surface to get the drag forces. Okay. So for streamlined objects, such as, remember that streamlined objects or streamlined bodies, okay, shapes or streamlined shapes have no separation, so no marked separation on the rear side of the flow, so of the object. So you can calculate the entire drag force to a good approximation using only the skin drag. The form drag is usually negligible, but if you consider bluff bodies, then like a sphere or a cylinder, then it is not easy to calculate the drag force on a sphere or a cylinder only using the bound layer theory. The reason is because, as I have been mentioning, you know that as the fluid flows from point A to point B, the pressure goes from a maximum to a minimum, while the velocity goes from 0 to a maximum. From B to C, the pressure goes from a minimum to maximum. So B to C is a region of adverse pressure gradient. So as a fluid particle which moves from B to C, okay, it moves by virtue of its kinetic energy, and that is being converted to pressure head according to the Bernoulli equation. But Bernoulli equation does not have viscous effects. In reality, close to the solid surface there is a bound layer, and there will be viscous effects which will tend to retard the fluid particle. At some point the particle will come to a stagnant case, and then it will be washed away by the surrounding flow. So, this region of recirculating fluid flow is called the wake. Okay. This is called the wake, and the boundary layer theory fails here because no longer the viscous effects are confined only to a small region close to the solid surface. It is actually a very macroscopic region comparable to the size of the sphere or cylinder itself. Therefore, the simple boundary layer analysis that is designed to work for streamlined objects without separation does not work for bluff bodies. So, when you consider flow past bluff bodies, like cylinders or spheres, bluntly shaped objects, okay, then the boundary layer theory is not enough to compute the drag force from first principles because of this phenomenon called separation. Suppose you consider, okay, a flow past a cylinder, let us say, and this is the potential flow velocity profile, which is completely symmetric about the fore and aft of the cylinder. Okay, this is a potential flow velocity profile, but what happens in reality is that when you consider a fluid particle which goes from here to here, it is facing favorable pressure gradients. The pressure is decreasing as it goes, but when it goes from here to here, it is facing adverse pressure gradient. So, the particle comes to a standstill at some point because of the viscous effects close to the boundary layer, and it gets washed away. Okay, the flow profile, actual flow profile will look like this, and this region of increased circulation is called the wake. Okay, this is called the wake. Now, what is interesting about the wake is that it completely alters the picture that the boundary layer where viscous effects are supposed to dominate is only a thin object, because the entire region of the wake viscous effects are important. Okay. So, this actually for bluff bodies, therefore, the picture that the boundary layer is a region of very small thickness compared to the object's dimension itself is valid only before separation, and the moment the flow separates from the body due to adverse pressure gradients, therefore, the boundary layer picture breaks down drastically. And what is important is that now the force on the object is dominated not just by the skin friction, which is due to the shear stresses on the boundary layer, but it is also dominated by the difference between the pressure on the fore and aft side, and that imbalance in pressure causes a huge contribution to the drag force, that is called the form drag. Okay, as opposed to skin drag, which is due to wall shear stress. The form drag is due to the pressure differences across the fore and aft of the body. Skin drag is due to wall shear stress. Okay. Now, therefore, in order to calculate what is the drag on objects such as spheres or cylinders, it is not just possible to do theory or analysis alone. You have to do experiments, and experiments, if you remember, we did dimensional analysis, tell the drag force in terms of a non-dimensional drag coefficient, which is nothing but the drag force F divided by half rho v squared d squared. Okay, where if d is the diameter of a sphere, okay, then that is the drag coefficient. It's called the drag coefficient. And we found from dimensional analysis a few lectures back that CD is a function only of the Reynolds number, where Reynolds number is rho v d by mu based on the diameter of the sphere and the free stream velocity far away from the sphere. Now, the Reynolds number we know is a measure of inertial stresses to viscous stresses in the fluid. It is a ratio of inertial to viscous stresses in the fluid. Therefore, CD is a function of Reynolds number. When Reynolds number is very, very small, you would expect that the inertial effects are much small compared to the viscous effects, and therefore, we can make an approximation. If you remember the Navier-Stokes equation, we have rho partial v partial t plus v dot del v is minus del p plus mu del squared v. Let us not worry about gravitational body force effects now. Now, when the Reynolds number is small, the inertial terms are very small compared to the viscous terms and the pressure forces. So, this can be neglected, and this equation, these are called the Stokes equations. That is, you just set the balance between inertial and pressure forces in the flow. So, you get mu is 0 and subject to, of course, the mass continuity, mass conservation equation, pointwise mass conservation equation. So, when the Reynolds number is very, very small, okay, these equations can be solved to find what is the force on a sphere or a, okay. Now, that results in the famous Stokes drag law. The drag force experienced by a sphere moving with a constant velocity u, sphere of diameter d, in a fluid of viscosity mu and density rho, is the celebrated Stokes drag law. F is equal to 6 pi a eta u, or if I use mu for viscosity. So, mu is the viscosity. Okay. So, this is the Stokes drag law, valid at very, very small Reynolds number. Okay. Importantly, it is the density of the fluid drops out of the equation, and that is because the fact that we have thrown away inertial terms in the fluid. Therefore, that means that density will not play an important role anymore. Therefore, the force is a function only of the instead of AL-ish we should put d, diameter, viscosity and the free stream velocity, and 6 pi is a numerical constant. Okay. Therefore, if you want to calculate what is the drag coefficient, we have to simply divide the force by half. CD is half rho u squared d squared. Okay. So, I mean, let me redefine my times the area of the sphere, pi d squared by 4. Dimensional analysis will tell you that it's simply half rho v squared d squared, but conventionally it is defined like this. So, pi d squared by 4. If we do that, if we substitute 6 pi d mu v by half rho u squared by 4, then the pi goes off. Okay. One factor of u will go with one factor of u, one factor of d will go with one factor of d, to give CD is nothing but, and so you will also find that this is nothing but, let us do the algebra, mu by rho u d, okay, times, so this half should not be there in the definition, it is rho u squared d squared times pi d squared by 4. So, you get this 4 goes above to give times 24. So, CD becomes 24 by Reynolds number. So, the drag coefficient is defined without the half, rho v squared times the area. Okay. So, that becomes 24 by Reynolds number. Okay. So, this is the drag coefficient when the Reynolds number is small compared to 1 at the when the inertial forces in the fluid are negligible. So, when we do experiments, therefore, if you plot log CD, log of the drag coefficient versus logarithm of the Reynolds number, okay, initially when the Reynolds number is less than 1 or 10, okay, it will be a straight line with slope -1 because CD is inversely proportional to Reynolds number. Now, after that the CD will appear like this, there will be a zone of constant drag, and then suddenly the drag decreases at a Reynolds number of 10 to the 5, is about 10. Okay. Now, here the sudden decrease is because of the fact that there is a transition from laminar flow to turbulence. Okay. The flow, the boundary layer past the sphere, it has become turbulent. Okay. As in any case, as in any flow, when the Reynolds number increases, for example, many flows are susceptible to this transition from undergoing from laminar to turbulent flow. So, this also does that. Therefore, you do find, but what is interesting is you find a decrease in the drag coefficient, a sudden decrease in the drag coefficient that marks the transition from laminar to turbulent flow, and that is because of the fact that the separation in a turbulent flow is delayed compared to laminar flow. Okay. So, remember that the drag coefficient, drag forces on blunt bodies like spheres and cylinders are determined by the flow separation, and if the flow separation happens early on the surface of the sphere compared to late, then the drag will be more. It turns out that in turbulent flow the separation is delayed, and therefore you find a lesser drag in turbulent flow compared to laminar flow. So that is some peculiar feature of laminar turbulent transition, peculiar feature of drag forces on blunt bodies such as flow past a sphere, that there is a sudden decrease in drag when the flow undergoes the transition from laminar to turbulence, because of the fact that the separation is delayed on a turbulent flow compared to laminar flow. For example, in a laminar flow, if you measure the angle from the upstream, so the separation occurs at an angle of 82 degrees, while in a turbulent flow, okay, it happens at an angle of 120 degrees, the separation. So when the separation is delayed to the rear of the sphere, then the extent of pressure asymmetry, the form drag is reduced when you have a turbulent flow past a sphere, thereby leading to lesser drag in a turbulent flow compared to laminar flow, which is at a first sight it appears counterintuitive. In fact, it runs counter to our normal intuition that turbulent flow should have more drag, but here the reason why the drag is reduced is not because of reduction in skin friction, but it is in fact due to the reduction in the form drag because of the fact that the separation is delayed on a turbulent flow past a sphere. So that is the reason why we have lower drag in a turbulent flow compared to laminar flow. Okay, and so when you want to prevent separation, you have to do what is called streamlining. When you want to prevent this increased drag due to separation, that is because of this bluntness or the bluff nature of the bodies, the flow separates, okay, and that leads to a huge form drag. But if you want to prevent separation, we end up in what is called streamlining, wherein you do not allow the flow to separate, and therefore the form drag contribution to the total drag becomes negligible. Although now since we are increasing the surface area because you are now elongating the object, the skin drag contribution will be more. So there has to be a balance between these two opposing effects, that is, while on the one hand form drag is reduced, on the other hand you are trying to increase the skin drag, but you can always strike a balance and then find that at some values, intermediate values of the shape of the body, streamlined body, you do find a total decrease in drag because you have now effectively removed the form drag at the cost of some small increase in skin drag. So this is called streamlining, and this is used in many applications such as the design of airplane wings, wherein you do not want increased drag on the airplane wing, which helps you to lift the airplane, but you don't, at the same time you don't want the drag to be more. So you streamline the shape of the airplane wing so that the drag is less, and the same goes in the shaping of various automobiles such as cars and so on. As long as you have streamlined body, okay, the drag force, the resistance force experienced by the moving car or moving automobile is less compared to when the case when there is no streamlining. So this is the fundamental reason behind shaping of objects when they move in flow, especially at higher Reynolds numbers, because you are trying to prevent the form drag loss in such objects by making the object shape in such a manner that they are streamlined and there is no separation that occurs. Okay. Now, so far in this course we have been discussing very many fundamental issues in fluid mechanics. That is, we have discussed first of all integral balances of mass, momentum and energy, and then we proceeded to discuss differential balances of mass, momentum, and leading to the Navier-Stokes equations, and we worked out various solutions of the Navier-Stokes equations in simplifying approximations, using simplifying approximations. Then we moved to dimensional analysis as the third way of solving problems in engineering fluid mechanics. That is, when you cannot solve all problems using differential balances, you have to use you have to take recourse to experiments wherein we have amply demonstrated that dimensional analysis will play a very important role. Now then we moved on to this analysis of pipe flows and fittings and losses in pipe flows using the friction factor charts, and finally we also discussed various topics in higher Reynolds number flows such as potential flows, Bernoulli equation, solutions for potential flows using superposition principle, and finally we moved to bound layer theory, which led to the notion of which led to the calculation of drag force on objects such as streamlined objects such as airfoils or cross sections of airplane wings, and then we also discussed the notion of separation in bluff body flows. Now the next remaining lectures of this course, we are going to focus on applications that are closer to chemical engineering and the applications of fluid mechanics in many chemical engineering operations. See, the fundamentals of fluid mechanics are general and they are as applicable to chemical engineering applications as to any other applications. Of course, we did focus a lot on applications even before, when we discussed pipe flows and losses, when we discussed flow measurements using various orifice or venturimeters or pitot tube. They are all applications that are related to chemical engineering, but now we are going to look at some contexts of fluid mechanics which are peculiar only to chemical engineering, and then we will see how we can make useful approximations, suitable approximations, and tackle those problems. We will continue that in the next lecture.